You've heard all the buzz, right? About the latest AI models, the ones that seem to, well, think things through step by step before giving an answer.
Uh-huh. Large reasoning models, or LRMs,
Huh.
they really push that idea, generating these detailed plans or chains of thought.
Exactly. And it looks impressive. Like they're getting closer to actually, reasoning. Models like Claude 3.7, Sonnet Thinking, or DeepSeek R1.
Yeah, they're built specifically for that, generating those long intermediate steps. Sometimes they even seem to self-correct along the way. And you see them do well on tough tasks, standard benchmarks.
Mm.
It really looks like thinking.
But okay, here's the question, isn't it? How do we really know? Are they genuinely reasoning or just getting like incredibly good at mimicking the appearance of reasoning?
That's the core issue.
Uh-huh.
Because the usual ways we test them, standard math problems, coding challenges, they have some pretty big blind spots.
Blind spots how?
Well, for one, data contamination is a real worry. These models train on just enormous amounts of web data. So there's a decent chance they've already seen the exact problems, or maybe very similar ones, from the benchmarks we use to test them.
Ah, so they might just be remembering the answer, not figuring it out, like they peeked at the answer key.
Exactly. It looks like success, but it's memorization, not problem solving. And then there's the other thing. Even when they do show their work, generate those steps.
Yeah.
Most benchmarks just score the final answer. They don't really look at how the model got there. That whole internal thinking trace, the step-by-step process, it's mostly a black box in standard evils.
Okay, so potential memorization, plus we're not checking the work properly. That makes it really hard to know what's actually going on, especially when things get complicated.
Precisely. We need a better approach if we want to understand their real capabilities and, importantly, their limitations.
So if standard benchmarks aren't quite cutting it for probing real reasoning, where we go? Which brings us to the research we're digging into today, right?
Yes, exactly. This paper takes a really interesting detour. Instead of standard benchmarks, they use these controllable puzzle environments.
Puzzles, like logic puzzles.
Sort of, yeah. Classic ones, but chosen very carefully. Things like Tower of Hanoi,
Oh, yeah, moving the disks between pegs.
that's the one. And checker jumping, river crossing puzzles, the fox, goose and beans kind of thing.
Well,
At blocks world, stacking blocks. They all need logical, sequential steps based only on the rules you give them.
okay, I can picture those. Why are these puzzles better for testing reasoning than, say, a huge set of math problems?
I have some key advantages. First, you can control the difficulty really precisely. Add a disk to Tower of Hanoi, it gets harder. Add checkers, same thing. So you can map performance very neatly against complexity.
Okay, fine-grained control. What else?
Second, it helps a lot with that data contamination problem. You can generate totally new puzzle instances on the fly that the model almost certainly hasn't seen before.
Right, so you're forcing it to solve something fresh, just using the rules provided.
Exactly. No phoning a friend, no looking up answers. It has to be algorithmic, based only on the rules. And maybe the most crucial part for this research.
Yeah.
You can automatically check every single step the model makes using simple simulators for these puzzles.
Oh, wow. So you can actually validate the entire thought process, not just the final move.
Precisely. You
Yeah.
can really look inside that reasoning trace and see if it holds up.
Okay, this sounds like a much more rigorous way to test things. So the goal here is use these puzzles to see what really happens with LRMs when the going gets tough, find out their strengths, where they just hit a wall, and what that internal thinking actually consists of.
That's the mission. Get past the hype and see the underlying mechanics, the good and the bad.
All right, let's dive into what they found. They compared these thinking models with regular LLMs on the puzzles. And the relationship between performance and difficulty, it wasn't straightforward, was it?
No, not at all. They found basically 3 distinct phases, or regimes as they called them, based on how complex the puzzle instance was. They compared LRMs like the Claude 3.7 Sonnet Thinking and DeepSeek R1 against standard versions, making sure they had similar compute budgets.
Okay, regime 1. What happens when the puzzles are easy? Low complexity.
This was actually pretty surprising. For the simple stuff, requiring just a few steps, the standard non-thinking models were often better, more accurate.
Wait, the non-thinking models were more accurate on easy problems?
Yeah, and they were definitely more efficient, used way fewer tokens.
So the models designed for thinking were less accurate and use more resources on easy stuff. That seems backward.
It does, right? It's like the LRMs were trying too hard, generating internal steps for problems that didn't need them. They seem to overcomplicate things and maybe get tangled in their own thoughts, while the standard model just, spat out the simple answer.
Okay, so more thinking isn't always helpful if the problem's trivial. What about when it gets a bit harder? Medium complexity.
Right, the second regime. This is where the puzzles need a decent number of steps, more than just simple pattern matching, but they're not insanely hard yet. And this is where the LRM started to shine.
Ah, so the extra thinking starts to pay off here.
Exactly. Their ability to generate those longer chains of thought, explore possibilities internally. It allowed them to consistently outperform the standard LLMs in this middle range of difficulty. The gap really opened up there.
Okay, so thinking hurts on easy, helps on medium. What about the really tough problems? High complexity.
And this is maybe the most striking finding. The third regime, high complexity. Here, it didn't matter if it was an LRM or a standard LLM. It didn't matter if they gave it a huge token budget to think with.
What happened?
Performance just collapsed. For both types of models. Accuracy plummeted to basically zero across all the different puzzle types once they crossed a certain complexity threshold.
A total collapse, like hitting a wall.
A very sharp wall, yeah. Accuracy hit 0% or maybe 1%, just gone. The thinking models might have pushed that wall back a tiny bit, maybe solved slightly harder instances than the standard ones.
But they still hit the same wall eventually.
They hit the same wall.
Yeah.
Complete failure.
Wow. That's a stark limitation. And wasn't there something else really weird related to this collapse? Something about how much they think right before they fail?
Yes. This is one of the most counterintuitive results in the whole paper. You'd naturally think, okay, problem's getting really hard, the model's going to try harder, right? Generate more steps, think longer, really work at it.
Yeah, makes sense. Throw more computational thought at the problem.
But they found the exact opposite. As the puzzles got harder and approached that failure point, the LRMs actually reduced their thinking effort. They generated fewer thinking tokens.
They think less when the problem gets harder. Seriously, why on earth would they do that?
It's baffling, isn't it? And it wasn't because they ran out of tokens. They still had plenty of budget available. They just seemed to give up sooner or generate shorter, less complex thoughts.
So what do the researchers think is going on there?
They suggest it points to a fundamental inference time scaling limitation. It's not just about having enough space or tokens to think. It's like their actual ability to generate useful, coherent steps starts to break down when the problem gets too complex. The cognitive load gets too high, and they sort of retreat, producing less output.
Huh. So the bottleneck isn't just memory or compute time in a simple sense, but something deeper about how they handle complexity. Like their internal strategy just fails.
That seems to be the implication. It's a limitation in their core processing or reasoning strategy when faced with very intricate problems, not just a capacity issue.
Okay, so let's look inside those thoughts. You said they could actually check every step the model generated using the simulators.
Yes, which is super insightful. They could see the sequence of moves or states the model considered internally and check if each one was valid according to the puzzle rules. And they found different patterns depending on the difficulty.
Right, so back to the easy problems, where the thinking models were surprisingly inefficient. What did their internal traces look like?
Well, often, for the simple problems, the model would find the correct solution, the right sequence of steps, pretty early on in its thinking.
Okay, so it gets the answer.
But then it wouldn't stop. It would keep generating more steps, often exploring and validating incorrect paths after it had already found the right one.
Huh. So it solved it, then kept thinking about wrong ways to do it. Classic overthinking.
Exactly that. The accuracy within the thought trace would actually go down or just bounce around after hitting the solution. It's just inefficient. Burning compute cycles, exploring dead ends after the race is won.
Okay. And the medium problems, where the LRMs did better.
For medium complexity, the pattern was often reversed. They'd tend to explore incorrect solutions first. Lots of invalid moves or states early in the trace. And the correct path, or parts of it, would only start to emerge later in the thinking process.
So it's like they're fumbling around internally, trying things out, and eventually stumbling onto the right track.
Kind of, yeah. It suggests some kind of internal trial and error or maybe even a rudimentary self-correction happening. The accuracy within the trace tended to increase over time for these problems, as they hopefully converge towards a valid solution.
Right, until they hit the wall, the high complexity zone.
And at high complexity, the traces just confirm the total failure. The models simply couldn't generate any valid, complete solution path within their thoughts. Accuracy inside the trace was basically zero, right from the start, right to the end.
Nothing useful happening internally at all.
Pretty much. No matter how many tokens they spent thinking, they never found the correct sequence.
Wow, seeing inside like that really changes the picture. It's not some neat logical deduction always. It can be messy, inefficient, or just completely broken.
It really highlights both the potential, like that internal search for medium problems, but also the very real inefficiencies and ultimately the hard scaling limits.
Now, you mentioned some findings that were really, truly puzzling. Things that kind of break our assumptions about what these AIs should be good at.
Yes, a couple of results were particularly eyebrow-raising. The first one has to do with following instructions, basically, exact computation.
What did they test?
Okay, so for the Tower of Hanoi puzzle, right, they didn't just ask the model, solve this. They actually gave it the correct algorithm.
Like step-by-step instructions.
Exactly. The standard recursive algorithm for solving Tower of Hanoi was put right there in the prompt. The model's job was just to execute those steps for the given number of disks.
Okay, wait. Giving it the recipe and just asking it to follow the instructions, that has to be easier than figuring out the recipe from scratch.
You'd absolutely think so. I mean, planning and finding the algorithm is the hard part, right? Just executing steps should be much more straightforward.
So did it ace it then?
Nope.
Hmm.
That's the shocker. Providing the explicit algorithm didn't really improve performance much, if at all.
Seriously.
Seriously. And that complete collapse at high complexity, it still happened right around the same point, even when the model just had to follow the provided steps.
I don't even know what to make of that. They can't reliably follow a clear, logical set of instructions given to them.
It certainly seems to point that way. It suggests a potential weakness, not just in finding solutions, but maybe in the basic ability to perform precise, step-by-step symbolic manipulation or consistently follow logical rules, which is, pretty fundamental to what we think of as reasoning.
Yeah, if executing instructions is a struggle, that feels deep. Were there other weird inconsistencies?
Yes. The other really surprising thing was how inconsistent the models were across different types of puzzles. They looked at one model, Claude 3.7 Sonnet Thinking, and measured how many correct moves it could make in a row before its first mistake on different puzzles.
And big differences.
Huge differences. For example, on a complex Tower of Hanoi puzzle, maybe with lots of disks, the model could sometimes make over 100 correct moves consecutively. Really impressive accuracy for that task.
Okay, so it's great at Tower of Hanoi.
But then, they tested it on a river crossing puzzle. A simple one, NPE3, only needs 11 moves total to solve optimally. And the same model would often fail after making just 4 correct moves.
4 moves after doing over 100 right on another puzzle. That's incredibly inconsistent.
It really is. And it strongly suggests performance isn't just about the raw logical complexity or the length of the solution.
So what could be causing such a difference?
The researchers suspect it might have a lot to do with the training data. Maybe examples of Tower of Hanoi, even complex ones, are all over the internet and were heavily represented in training. But maybe river crossing puzzles, especially ones with more than 2 people or items, like N3 or higher, are just much rarer online.
So the model looks like it's reasoning well on Tower of Hanoi because it's seen patterns like that before, but faced with a logically simpler but less familiar type of problem like river crossing, its supposed general reasoning ability just falls apart.
That's a plausible interpretation, yeah. It challenges the idea that these models have developed a truly general, robust reasoning skill that works equally well across different kinds of logical tasks. Performance might be unexpectedly brittle for problems that are perfectly solvable, but just haven't appeared much in the training data mix.
Okay, let's try and wrap this up. What are the big takeaways from this deep dive?
Right. I think using these puzzles gives us a much clearer, maybe less flattering picture of current LRMs.
So takeaway 1, generating thinking steps helps, but mainly just for medium difficulty problems. It can hurt on easy ones, and it completely fails on hard ones.
Yep. And that failure is a hard wall, a collapse. And weirdly, they seem to reduce effort right before they hit it, suggesting some kind of core processing limitation kicks in.
And looking inside those thoughts shows it's not always pretty. Overthinking on easy stuff, maybe some useful trial and error on medium, but just nothing on the hard problems.
Exactly. And then the really surprising bits. The struggle to even follow explicit instructions reliably.
Yeah, that Tower of Hanoi algorithm result is still baffling me.
And the wild inconsistency across different puzzle types, which hints that maybe it's more about familiarity with training data patterns than true general logical skill.
So for anyone listening, if you're using these models or trying to evaluate them, what's the message?
I think it's a big caution sign. Their abilities aren't monolithic. They don't just scale smoothly with complexity. Success on one type of problem or one level of difficulty doesn't guarantee success elsewhere.
And just looking at the final answer isn't enough.
Definitely not. You need to understand how they're trying to solve it, where their process breaks down. That's key to knowing how much you can really trust them, especially for complex, critical tasks.
It really makes you question what we mean by reasoning in this context. Are they reasoning, or are they just incredibly advanced pattern matchers that sometimes produce outputs that look like reasoning?
It definitely complicates that narrative. The picture is much more nuanced.
Okay, so here's a final thought to chew on. If giving these models the exact algorithm doesn't stop them from failing when the problem gets complex enough, what does that truly imply about their ability to handle symbolic logic and execute sequential instructions? Is that a fundamental flaw in today's architectures, like transformers? Or are we just missing the right way to train them or prompt them to unlock that kind of reliable step-by-step execution? It feels like there's still a pretty significant gap between what we have now and building machines that can truly reason robustly.